we do the first steps towards a type checker. My goal is to save the type of expressions in the abstract syntax tree. What we want to implement in near future is record field access, but it has one problem. So basically, if I just have a record R and I want to access the field F, and for example assign a value to it, then if we have only this syntax, so R is just a variable, it's pretty simple. So I have all variables and their types in the symbol table, and I just have to do a lookup into the symbol table and read the type of this variable, so I can see where the field F is, and I can calculate the offset in the variable, so I can assign a value to it. But a lot of our records are not directly variables, but they are pointers. So basically in the most cases we have now, we have dereferencing, so R is a pointer to a record. We need to dereference this pointer and then access a field on it. But if we dereference a pointer, then we have an expression on the left side, and we can't just look up it in the symbol table. So we need to know the type of the expression. And therefore, we want to decorate our syntax abstract tree with a type, so the types of all expressions are saved in the tree itself. It also will have help with the type checking, because we can compare types of different expressions. For example, that expressions on the left and right side of an binary expression are compatible with each other, and similar things. So basically I already introduced field type decoration in all expressions in the abstract syntax tree, and I extended the type check-in pass to iterate other expressions, but I haven't finished it. So we will go to the type checking functions, and they start with the prefix Elna type. And I wrote I wrote the function that goes through the if statement and checks all if conditions and statements inside of if, and I have empty functions or empty procedures for the other kinds of statements. And we are going to split the screen so I can see how what fields do these statements have. And the first one is this return statement. I think if statements is complete. Yeah. So return statement. Let us look at the definition of the return statement. And return statement has just a single expression it is these returned expressions. So returned expression, we define a new variable and we read the value from this return statement. So it is, our records already support field accesses, but this field access is done with automatically generated getters and setters. So for example, to get a field returned from the return statement, I just have to write return statement get returned and pass the record to it. And we want to replace basically this thing with normal record access. So I can just write returned, but it isn't currently supported, but it's our goal to implement it someday. probably not today, but soon. So we got the expression from the return statement and we just have to visit this expression with our type checker. It's basically binary expression and returned expression, and it is everything we need. The linker says that the function doesn't exist. Oh, it's actually wrong. In the if statement, I just visit the statements, but I don't visit the expressions because I haven't implemented the procedure for it at all. I think even if I look for ELNA type, anything expression, I won't find anything. So we don't have a procedure for it yet, but we define just an empty procedure and put it in here. Binary expression, so this one visits the binary expressions. The binary expression is the most complex expression in the current implementation of the language. So we begin with this binary expression and now it should compile basically. Yes, it does. And I think that return statement is now finished. We just get the return statement and visit the expression inside it, and we need to visit the expression in the condition of if statement. We can just say ELNA type binary expression condition. That's it. So now we only have the assign statement and call statements or call expressions. We begin with assign statement. So assign statement has two variables that are interesting for us, assignee and assignment, but they are not the same. Only the assignment is a binary expression. It is the right side of an assignment, and the left side of an assignment can contain also an expression, but it is not a binary expression, but it is a so-called designator expression. So this is basically a thing like dereferencing. Let us define two variables, and in the correct procedure LHS Word und RHS Word, and we assign values to them. Assign statement get assignee from the parser node, and the same with the right hand assignment from the parser node. And for the assignment we need to visit a binary expression, so it's elnode type binary expression parser node. And for the left side it's a designator. We don't have a procedure for it yet. Exactly, it's basically this thing. So we go to elnode type binary expression, and we create a new empty procedure called elnode type designator. We pass an ast node to it, and it is empty for now. And here we visit this node with designator. So that's done, and now we have the most interesting part. These are the call expressions, and I can't find them at all. Okay, we are going to look where is tree kind call used. Set kind call size. Oh, I don't have a record for it, but I just use a block of memory of 44 bytes. And my procedure can have only 7 arguments at most, I think. Yeah, and the arguments are saved in an array. Yeah. Call set arguments. And the last argument is probably set to 0 to nil, so I can see how many arguments does the procedure call has. So what do we need? We have a call and we have functions like get argument mit n, and what we need is basically a variable like current argument, and we begin by just getting the value of the first argument. So it is argument is call get argument. We pass the procedure call node to it, and we want to get the first argument. And now we want to check whether this argument is 0. If this is the case, no, we are probably not interested if it is 0. If it is 0, we do not want to do anything with it. We want just to exit the procedure. So we actually check if the argument is not 0. In that case, we want to visit the abstract syntax tree for this argument. So we call enna type binary expression current argument. This is the one thing. And we will rename this or define an additional variable, and we call it argument tree, for example, and we change the usage of current argument to argument tree. So, and now we will say that current argument is 1, and we say that we want argument number current argument. So after that we increment the value of current argument. So we say current argument is current argument plus 1, and we want to define a label here. So our language will have the loops someday, so something like a while loop, but since they are not implemented yet, we use goTos with labels, and we define a label in a type call argument. So to define a label, we write a dot at the beginning of the statement, and then the label name, and then we can jump to these labels with goTos, and we just write the name of the label, but without the dot at the beginning. So it's basically argument, yeah, and it jumps to the beginning again, takes the next argument, visits it if it is not 0, and goes to the next argument, and this can basically be nil. Exactly. That was it for the visiting of the statements. So it should be enough to visit all statements in our language. Now we can move to visiting the expressions, and we defined an empty procedure binary expression. Binary expression, so the node that we have here, it can be a binary expression, but it can also be a simpler expression. So we define a variable expression kind, and we get the kind of the expression that we have gotten here. So expression kind is ELNA3 node, I think, get kind, and we pass parser node to it. If the kind of this expression is ELNA3 kind binary expression, then we are going to handle it here. Otherwise, we pass this expression to the next visitor, and this visitor will be ELNA type unary expression, and we pass the parser node to it, and I need to define this function first. So we write procedure type unary expression parser node word begin and end. I'll not kind binary expression. This is fine. Elementary node get kind looks fine as well. Expression kind. Oh. Exactly. So now we have this ELNA type unary expression, and for the unary expression, the same is valid. It can be unary expression or it can be a simpler expression. So we basically want to take the expression kind of this expression once again, and we just say that expression kind is basically ELNA3 node get kind parser node if expression kind is ELNA3 kind unary expression, then we handle it. Otherwise we pass it further. I think that the next level is designator. We can look it up. So we go to the designator parser and we go to the unary expression, and unary expression parses an operator for the unary expression and then calls ELNA parser designator. So designator is basically the next level expression, and if this one is not a unary expression, then we pass this node to the designator, a procedure, an empty procedure for the designator. We have it already, so we just call it and a type designator, and we pass the parser node to it, and we try to compile this thing again. That seems to be fine. The same game here. Expression kind is, and if I think that the designator expressions are already a bit more complicated. So I have only unary expressions for So all unary expressions are basically the same expressions, and we just have an operator. So let us look at them. I think it's unary expression already. It has a kind, and it has operator as a field. But for the designator expressions, we don't have a designator expression as a separate expression, but actually designator expressions are pointer dereferencing, and it is also array access, I think, but we don't have arrays currently, so I think that the only designator expression is that is actually possible is actually not the only. It can be dereferencing and it can be field access. So these are two types of expressions that are possible as designator expressions. So basically we need to check if expression kind is ELNA3 kind dereference expression, then it can be ELNA3 kind field access expression, then, and if it is not, then it is a simple expression. So we define a procedure type simple expression parser node word begin and end, and otherwise we call this simple expression procedure and pass the parser node to it. A simple expression is basically a literal. I don't know if we want to create separate function for all literals, so simple expression so this is here these are basically the types of the possible types for a simple expression. So it can be character, string, or integer literal. It can be a nil literal, or it can be a variable expression. Actually, we can write separate procedures for it, I think. ELNA type nil. Do we have something like this? No. Or for example character. Yeah, we can define separate functions, so we have smaller procedures. I think it is a good thing. So let us define what's ELNA type character literal. They all will do the same thing currently. By later they will assign different types to the expressions, because of course characters and integers have different types in ELNA, but we don't have character at the moment, so it will do the same as integer and nil, but later they will be absolutely different. Not absolutely, but different, let us say. So parser node word begin and end. we check if the compiler compiles. And we make a few copies of it. So we have character literal, we have integer literal, we have string literal, we have nils, and we have variable expressions. Actually, I don't like nil. It should be really called nil literal. But well, variable expression. Variable expression is just the variable name. I call it expression to distinguish between variable declaration and variable expression. Variable expression is just the variable name that can occur inside an expression. So we have all functions here. Now we can define expression kind variable in the simple expression, and we can assign the appropriate value to it. So we say elna3 node get kind parser node, and we check its value. Expression kind can be elna3 kind integer literal, then we visit elna type integer literal parser node, then it can be character literal, character, character, it can also be a string. It can be null, and it can be a variable expression. That's it. So at this point, if we get into the elna type character literal, we know that parser node is a character literal, and we can set its type. So elna3 character literal, and we need, of course, yeah, set what was it, type decoration, and we set it to in the parser node to nil, because I don't have the type yet. So the word type is saved in the global symbol table. So first we need to look up the type. Symbol type is a word. So symbol type is symbol table lookup symbol table global. So we have two symbol tables, a global symbol table and a local symbol table. So local symbol table is a table belonging to a procedure for defining local variables and such. We are interested in the type called word, since it's everything that we support currently on primitive types and basic types, and word is 4 bytes long. So it is actually planned that strings in this language are a string pointer, so a character pointer, and its length, but it isn't implemented yet. So to pass a string with its length, we do it manually, but it is planned that it is done automatically. So Elna won't have 0 terminated strings, but it will have strings as a small record, so string pointer, and the length of the string. Let us see if the lookup succeeds. It looks fine. Let us introduce one more variable. So we also define symbol info. The things that are stored in the symbol table, they are not directly the types, but there is also an additional type around it, so info, and the type is saved in the type info record. So the thing that we get here is actually symbol info, and we can then say that symbol type is it was actually type info. So the getter will be called type info get type from the symbol info, and this type then should be saved in the expression symbol type. This is what we want to have. So integer literal is the same, absolutely the same, since integers and characters aren't handled differently in the current at the current time. So we copy it and check if everything compiles. It does. The same for string literal. There are also no differences, so we copy it also here. Of course, the one thing that is incorrect, I use everywhere this L03 character literal. It kind of works because all literals and all expressions at all have the same structure. The with type decoration is the second field in the record, but actually it should be character literal for characters, but it should be, of course, integer literal for integers, and it should be string literal for the strings. Then we have nil. It's the same, and the type is called L03 nil, I think. It doesn't exist. Yeah, but that one I called nil literal, but the procedures on literal. And the variable expression will be more interesting because theoretically at the current time all variables have the same type, but actually we can't just write word, but we need to look at the type of the variable in this symbol table, and for that we have to pass the symbol table to these procedures so it can do the lookup. But first we are going to rename these functions because I really don't like this nil thing. I want to call it nil literal. So, and let us look for similar procedures. Elna parser nil is the same, it should be called nil literal. Exactly. Actually, nil will have the type called point, I think. So in C, the type for this thing would be probably a void pointer, but our language won't have anything that is called void, because it is actually something strange notation. So void designates no value, but there is a void pointer. We will just have a type pointer, and the type pointer will be a generic pointer that cannot be dereferenced by but that can represent any pointer. So we don't have any. I have this LNATAC null function nil procedure, and we want to rename this one as well. So TAC nil will be called TAC nil literal. And that was it. Now the symbol table. This one is interesting. Actually, I need the symbol tables also in other passes. I should look how I have passed it to the things like TAC. So basically all expressions have an additional argument, this symbol table argument, and our procedures will be the same. So let us look then for this. We have we have these type procedures here, and all character literal, integer literal, string literal, and nil literal, they do not call any other procedures, and they don't need a symbol table. But this element type variable expression needs a symbol table, so we add an additional argument, symbol table word. It should just do compile. So then we go to the symbol table and we define an additional parameter here. This is word, and we pass this symbol table to the variable expression. And then we go to the designator and we add a symbol table here as well, and we pass this thing to the simple expression. Then we have the unit expression, I think, is next. Yeah, looks like it. So we add symbol table here. This is word, and we pass this thing to the designator, symbol table. Then we have the binary expressions, so we add the symbol table, that, and we pass it in here, symbol table. What have I done? so it's fine. We do not need this semicolon here and here. So it is a binary expression. So let us see where ELNA type binary expression is called. And there are a few places. The first one is the return statement. Let us begin here because it is the most simple type of statement. So it expects a symbol table of the bird and it passes it further to this binary expression symbol table, and then we go to the ELNA type return statement, and this is this symbol table word. Now, return statement, I've forgotten, symbol table, then we go to the if statement, ELNA type if statement, and we pass a symbol table to it, and it should pass it further to the conditionals worker symbol table, and we also have an if statement here. Yeah, actually here as well, symbol table. Exactly. So let us look at this ELNA type statements. Thin, it needs an additional argument, symbol table word, and it passes the symbol table to the statement procedure. So where were we? Actually we need these conditionals. What was it? Type conditional statements, I think. Exactly. So symbol table that, and it goes into binary expression for the if condition symbol table, and it goes into get statements. I get the statements, but I don't visit them. Can it be? Yeah, looks like it. So after I got the statements, I then get the next conditional block in the list. So one conditional block is basically a pair of a condition and statements. For example, for if statement it is if condition and if body block, and it can be else if condition and body block. So each if statement contains a list of conditionals, where each conditional is an expression, and the statements that belong to this expression, it is done to represent this whole else if things. So else ifs are saved as as a list of pairs, where each pair is a condition and a statement list. Yeah. Elna type statements, and symbol table. So we visit the statements in the conditional block of an if statement. And we are done here, I think. If statement, and it passes symbol table to their own function. And type conditional statements. And it should also pass it to the else block. Exactly, and else block, because it doesn't have a condition, it is just a list of statements. So each if statement contains a list of conditionals for if and else if, and an optional list of statements for the else block. Then we have the return statement that is already done. Then we have this assign statement. It gets a symbol table and it passes this symbol table to the designator symbol table and to the binary expression on the right side and to the designator on the left. So this is already done. Let us look at the statement. So we pass the symbol table to the if statement, to the return statement, then we pass it to the assign statement, and we pass it also to the call expression or statement in this case, but I use the same structure for if statements and if expressions, but Elna doesn't support expression statements, so the only expression that I currently support that can also be a statement, it's basically a procedure call. A lot of other languages support any expression as statement and then just warn that the result of an expression is unused if it is if an expression is the whole statement. I was by a call. Exactly, symbol table, and we say it is a word, and we need to pass this thing just to each argument, so basically only here, and it should be probably be enough. So let us look at Elna type statements, or more exactly to where it is called. The one place is conditionals if statements, the other one should be procedure declaration. It can be that I don't call these functions at all. So symbol expression. Procedure declaration. We get the body. I visit them. I visit all the statements, but I write here the statement visit in loop once again. Actually, I want to replace this block with a single line. It should be Elena type statements, and we can pass body to it, and it should be pretty enough, I think. So, and just to be sure that these functions are visited, we add a comment to the output and we check if it is there. Yeah, so these procedures are visited. That's a good thing. We can then remove this again, and we can remove this thing. So, procedure declaration. In this procedure declaration, I think that we have here the procedure name. So yes, it has name, length is the name length, body is the list of statements, temporaries and parameters are not interesting for us, I think, but we need the name and length so we can access the symbol table. Because the local symbol tables are saved in the global symbol table, so there is a procedure info that is saved in the global symbol table with the procedure name, and from this table we can get the local symbol table for the procedure. So basically we need a local variable in here, symbol table of type word. We can assign a nil to this first and pass it to the procedure here. So just symbol table. And that's it. Name pointer is a word and name length is a word, and then we read this data from the procedure declaration ask node, so get name parser node and get length. Procedure info, and we say then that procedure info is symbol table lookup. We take the global symbol table, this is symbol table global, and the name of the symbol is pointer, and its length is name length. So the lookup for the procedure in the procedure table will return a procedure info. Let us find this type, and procedure info contains its kind. We don't need its kind because we know that this is a procedure info, but we need the second field in the record. This is the symbol table, so we can just say procedure info get symbol table, and we pass the procedure info as argument, and maybe it will compile. Exactly, and this procedure info, we pass it in here. Then let us go to the variable expression. So Elna type variable expression, and we define here a variable the same way. So we just say that variable info, and we look up this info in the symbol table. So we just say that variable info is basically symbol table look up in the symbol table. And what is the name? This is the name of the variable that we have in the abstract syntax tree. I actually not sure what it is. Variable expression, name, length, on type decoration. So it's basically the same name pointer and name length, and name pointer is Elna3 variable expression, Elna3 variable expression get name is the symbol table, nonsense, from the parser node, and length from the parser node as well. So we have the name and name length now, and we can pass it to the lookup procedure. Wow, it still doesn't crash. So we have variable info. We need actually the type of this variable. After such a lookup, the variable can be of two kinds. It can be a parameter, or it can be a temporary. and I see currently that I don't save the type information at all in this info object. But let us check that the lookup in the table works properly. So as I said, this variable info, let us define a variable kind of type word, and we basically assign. I can check properly the kind. I think that I have a generic info object. Yes, variable kind, and we can say info get kind from the variable info. I hope that it works. So it doesn't work anymore. That can mean that the symbol is probably unavailable or something similar. Let us just check. I have a debug code somewhere, just a small snippet I use for debugging, and we want to move it in here, and we hide this one again, and I would say let us print the variable info pointer. It seems to have a valid value, but there are cases. The last case, it is nil there, so it can probably find a variable. We can put it into a condition and just look how often it is nil. So we can basically say if variable info equals nil, then do this output, otherwise do nothing. Okay, not boot, but valid stage section, and we go to the beginning, and we have two cases where the symbol info, variable info, is nil. We can actually just print what variable is problematic, or yet now I have to think of the correct syntax. It was something like this, I think, where I want to print a string of a specific length. source code and compile strings per se. Of course. Now I see what is the problem. Of course, this the local symbol table only has the local symbols, but we have also the global symbols. So additionally, we have to look into the global symbol table to find more symbols. Okay, this is not bad. I just need to add an additional function probably that does a recursive lookup, because I have already implemented it somewhere so that I look into the both symbol tables, and I think that we have 2 at most, because Elna doesn't have any scopes in the sense. There will be probably something like if scope for different things, but for variables there are actually only 2 scopes. So there is the global scope and the local scope for the procedures, but the variables can be defined only at the beginning of the function, so we don't need more than 2 symbol tables at time. Actually, we can leave it in here for now. Or we can fix it. I mean, why not? Yeah, I can do a lookup here, or just find another place where I ask for the symbol table. Lookup symbol table. Lookup symbol table global. I actually don't see the other occurrence where I looked. Yeah, then the other case is probably a bit different. So when I generate the intermediate representation, I also have to look up a symbol, but for example, in this pass, in the type checking pass, I will handle global and local variables with the same, so I only need the type of the variable. But in the intermediate representation, they are not handled the same, because local variables are located on the stack and the global variables are located in the static storage, in the global storage, or in the executable. So they produce different code generation. Therefore, the lookup is also a bit different. That actually means that we can just write here that if variable info is nil, then just look it up in the another symbol table. So look it up in the symbol table global, pass name pointer and name length to it. We can remove this stuff from here, and after that getting the kind of the variable should actually succeed. So let us output variable info again. It is still nil for the source code. But source code is just a global variable, I think. Yes, source code is just a global variable. So it should actually be in the global symbol table. Symbol table lookup, name point, name, length. If variable info is nil, then variable is lookup in the other table, symbol table lookup. Okay, we'll look at this one later. We have a different problem currently, so we looked at this parameter info variable, and I want to add an additional field to it and to the temporary info. We can call it type, but type is a reserved keyword, so let us call it variable type. Variable type is word, and variable type is word. So now in the name, in the semantic pass, in the name analysis pass, where we create these info objects, we need to save the type in the info object, or we probably will do it in the type check-in pass. We will see. But I think that I'm going to finish for today. We done actually enough for one time, I think. So we wrote the whole code that iterates the asked and passes the symbol table around and visits all nodes we are interested in, and we just need to fix a few places here and there, and I suppose that we do it the next time.